This is your assignment. Extra credit. It goes on all year long. Now, wait a minute. What? What's wrong with this? What's the matter? Yes?
It's like so...
So what? There must be a word to finish that sentence. Someone help her?
Weird.
Weird. Crazy.
Hard. Bummer.
Bummer. Hard. How about possible? It's possible. The realm of possibility exists where? In each of you. Here. So you can do it.
That's me. That's me. And that's 3 people. And I'm going to help them. But it has to be something really big. Something they can't do by themselves. So I do it for them. Then they do it for 3 other people. That's 9. Do 3 more.
That's 27, so I'm not really good at math, but it gets big really fast, you know?
All right. A little articulation, please. Yes.
I think it's a good idea.
Sean?
It's stupid.
Adam?
It's the honor system. People blow off the honor system. So what? Just because you do.
Well, Trevor, the class seems to think that you've come up with an overly utopian idea. Look that word up in a minute.
Like, a perfect world?
Mm-hmm.
So?
Okay, folks, what we're going to start learning about today is exponential functions. You've heard me refer to exponential functions quite a bit. We've been in a linear world for a long, long time. But in the Math 1 class, we focus on 3 different types of functions. We focus on linear functions and build off of what you've learned in 8th grade math. And then we go into exponential functions. And last but not least, we do our quadratic functions, which will come up in a few weeks. So going back to this movie clip that we just watched, we can see that he starts out, he's just one person, and he decides to do a good deed for 3 new people. But in return, those 3 people have to do good deeds for 3 more people. And you can kind of see how this starts to multiply out. You've got 1 person, then 3 people, then 9 people. And if you think about it, how many people do you think would be in the next round of good deeds? And this brings us into exponential functions. All right, so whenever we learn a new function, we like to compare it to functions we already know. So something that's similar about linear functions and exponential functions is they either increase or they decrease. They don't go up and down and up and down. They do one or the other. So we know with linear functions, they increase when they have a positive slope and decrease when they have a negative slope. For exponential functions, they either increase or decrease also, but it depends on their multiplier. And I'll come back to that in a minute. So linear functions, how you know something's linear is it has a constant rate of change. In other words, if you were looking at a table of its data, it adds or subtracts the same number over and over again. The difference with an exponential function is it has a constant ratio of change. And what that means is that it multiplies or divides by the same number over and over again. It has a multiplicative behavior instead of an additive behavior. So going back up to this exponential function that's increasing, you see this little b right here, and that'll make sense when you learn the formula. But the b is the base, and the base is your multiplier. And anytime we multiply by a number greater than 1, like for example, let's say we multiply by 2, so we keep doubling, it's going to increase and get larger and larger. Where anytime we multiply by a number between 0 and 1, for example, maybe we half something over and over again, it's just going to get smaller and smaller and smaller. So that's why we have 2 types of exponential functions. We have increasing functions and we have decreasing functions. And we'll come back to that in just a little bit. All right, so going back to our movie clip, does this situation represent a linear or exponential model? Why or why not? All right, so going back to this situation, hopefully you can see that this is an exponential situation, because what is happening is if we were to continue this little diagram right here, each person then goes on to do a good deed for 3 more people. So therefore it multiplies by 3. So we started with 1 person initially. They do 3 good deeds. And then those 3 people do 9 good deeds. And then you can see the next one would be 27. And then if we multiply 27 by 3, that would be 81. We could organize this in a table for the round number versus the number of good deeds done for that round. And I'm going to come back to this in just a little bit after we learn a little bit more about the function. All right, so what is an exponential function? Notice that the key word in exponential is exponent. So that's a good way to recognize an exponential function. It is a function where the variable is in the exponent. So here's our basic formula right here for an exponential function. It is y equals a times b raised to the x power. But it has some contingencies there. It goes on to say where b is greater than 0 and b cannot equal 1. Okay, so let me explain a few little things, and then I'm going to show you some graphs to explain to you why the base has to be greater than 0 and the base cannot equal 1. Looking at this form, we're going to go back and compare to linear functions again. We know our basic formula for a linear function, the one we love, is that y equals mx plus b, where m is the slope and b is the y-intercept. We know that m gives us the behavior of the function. We know whether the function's increasing, we know whether the function's decreasing, we know how fast it's increasing, or slow it's increasing or decreasing, depending on, how steep the line is. So exponential functions are similar in that manner, except they're not lines, they're curves. So when we have an exponential function, y equals a times b to the x, a is actually the initial value. It is the y-intercept. It's where we start on our graph. Or in a real world problem, it's that initial value. Where b we refer to as the base because it is the value that's being raised to different powers because x is our variable. But ultimately what b represents is it represents the multiplier. So going back to what I was saying earlier about exponential increasing functions versus exponential decreasing functions. Anytime that multiplier is a number greater than 1, so in other words, the base is greater than 1, your exponential function is going to grow. It is going to increase. So we call that, All right, so we call that exponential growth. Think about it. If you multiply by 2 over and over and over again, whatever you have is going to double. If you multiply by 5 over and over and over again, it's going to be 5 times what it was. So it keeps getting bigger and bigger. Where anytime we multiply by a number between 0 and 1, it is going to decay. In other words, it's going to decrease. So we use these words, exponential growth, exponential decay. Would the function be increasing? Would the function be decreasing? All right, going back to our basic formula, y equals a times b to the x. The reason why a comes out to be the y-intercept is because think about the fact that we know anytime we have a y-intercept on any function, doesn't matter what that function is, x is 0. So if we use that fact that we know whenever we have a y-intercept, the value of x is 0, and we substitute that into this formula, y equals a times b to the 0 power. Well, we learned from our exponent rules that anything raised to the 0 power is 1. So that's really saying that y is equal to a times 1. And then, of course, anything times 1 is itself. So you can see that when we go to work out and try to find the y-intercept, we can see why the y-intercept ultimately comes out to be a. All right, a couple of other contingencies with this was that the base has to be greater than 0 and the base cannot equal 1. The reason for that is what it is it's telling the multiplier has to be a positive number. Whenever you have an exponential function, the base can never be 0 or negative, because if we just multiplied by 0 over and over again, we never go anywhere. And if it was negative, it would keep flip-flopping back and forth between negative and positive numbers, and we wouldn't get this nice curve that we see over here that I've drawn. The base also cannot equal 1. So I'm going to pull up Desmos real quick and show y'all why that happens. Okay, folks, if you would like to play with this, remember all you have to do is go into Desmos and you can type in any basic formula. We did this when we had lines, and now we can do this with exponential functions. Y equals a times b to the x. When you do that, it'll ask you if you want to add sliders, and I just clicked add them, and that's why it lets me have these sliders right here. Well, notice right now I have a set at 1 and I have b set at 1. Do y'all see how when the multiplier, the base right here is 1, that all it's done is graph a horizontal line? And that is because if we multiply by 1 over and over and over again, it's never going to increase or decrease because anything times 1 is itself. Watch, I can change the a value to whatever number I want, but the b value, with the b staying at 1, it never increases or decreases. So that's why exponential functions have that contingency that the base has to be greater than 0, but it also cannot equal 1. But watch what happens when I start increasing that base from 1. Do y'all see that exponential growth right there? Any number where the base is greater than 1, it is going to grow exponentially. I'm going to come right here and set that base at 2. And what that means is that multiplier is 2. Check out these points on there. So originally I've got the point 0, 1. When x is 0, y is 1. My next point is at, if I can get this to click right on it, is at 1, 2. That next point right here is at 2, 4. It's kind of hard to get it right stuck on there that you can see it. And then if you come up here, you can see when we're at 3, we're at 8. And why that is because every time we inch over 1 unit, we double wherever we were. So we're at 1, and then we go to 2, and then 4, and then 8. Watch if I type in this function real quick. Y equals 1 times 2 raised to the x. And I'm only typing this in so that I can then create a table so that y'all can see these values. So you can see that covers up what we've just shown. And what I'm going to do is I'm going to come in here and I'm going to click that bolt and I'm going to make it into a table so that you can see these values popping up. Look at what happens as x increases by 1. Look at those y values and how they start doubling. Something you'll notice when you look at this function is notice how it has like this tail on it over here. As we move to the right, it keeps doubling. So watch, if I kept pressing enter right here, look at how those y values just keep doubling and getting larger and larger. And that's why, and y'all have heard this a lot with the coronavirus going around, we say it grows exponentially because it grows so fast. And it doubles. It doesn't grow at a constant rate. It just doubles and doubles. So once it takes off, it really, really takes off. But if I was to go backwards in this, and I'm sorry, hold on, I didn't mean to do that. So if I was to go backwards with these numbers, instead of multiplying by 2 as I move to the right, I do the opposite operation, which would be to divide by 2. And so you can see that it gets smaller and smaller and smaller. I'm going from a half to a fourth to an eighth to a 16th to 1 out of 32 to 1 out of 64 to 1 out of 128. So if I keep halving as I go backwards, what happens is even though it looks like it's getting closer and closer and closer to 0, it actually never gets there. So this is why these exponential functions have like this tail on them. And we're going to learn a little special thing about that in just a little bit. All right, so let me close that back out and go back to playing with our sliders. So what happens when the base is a number between 0 and 1? So check this out, like if the base is 0.1, do y'all see how now the function's decreasing? Or let me make it a half, like 0.5. Do y'all see how it's now decreasing instead of increasing? So that's the whole behavior part. As the base, if the base is a number between 0 and 1, and remember it can't be negative, watch what happens. Like it just disappears if I try to make it negative or I try to make it 0 because that's not part of the definition. And we could fix that right on here so this only goes to 0, which we wouldn't use, and then we could have this go to like 10. Okay, but you can see how anytime your base is a number between 0 and 1, the function decays, and anytime it's a number greater than 1, the function grows. Something else we can play with is our a value. Remember we talked about just a minute ago that a is the y-intercept. So watch what happens as I increase a. Can y'all see how that y-intercept changes if I increase or decrease it? Let me make this an exponential decay real quick. I'm going to put it back at 0.5 if I can. We'll use 0.7, that's fine. See how the y-intercept's still 3, but it's decaying now, or I could make it 2, or whatever I'd like to make it, and make it 1, make it 2, around there. Our problem that we started with, what if we wanted to write a function to represent our pay it forward situation? And by the way, guys, that movie, Pay It Forward, is an old movie. It's really good. Kind of sad, but if you might be able to find it on Netflix or something if you'd like to watch it. We can see here that the y-intercept is 1 because we call this round 0 because when he starts this, he's the first person who starts it, and none of the deeds have happened yet. Someone doesn't do a good deed for him. He starts it. So that's that initial value or y-intercept. And then we can see, and the pattern is that it multiplies by 3 times 3 times 3 times 3. So looking at our formula, y equals a times b to the x, our initial value right here, that y-intercept, we know that anytime x is 0, that the y value is the y-intercept, would be 1, and the multiplier would be 3. So this function would ultimately be the function y equals 1 times 3 raised to the x. And because that initial value is just a 1, you might see it written y equals 3 raised to the x, where x would be which round of good deeds is happening, and y would be the number of good deeds happening in that round. All right, so how does this all connect to what we've been doing with all these exponent rules? We're going to go back to two very basic exponential functions. Y equals 2 to the x versus y equals 1/2 to the x. Notice I'm using functional notation just to separate them. One's f of x, one's g of x. Well, all we're doing, guys, is I've just made up x values just like you would with any function. I'm going to substitute them in for x and see what our y value is. So kind of think about that over here. Like if I substitute 0 in, what I'm really saying right here is I'm saying 2 to the 0 power. And we know that anything to the 0 power is 1. 2 to the first power. So that would just be 2. 2 to the second power. 2 times 2 is 4. 2 to the third power. So 2 times 2 times 2 would be 8. And you can see that when you look at these numbers, all that's happening is they're just doubling, because that's the whole point of this function. As we move up 1 in x, our y values double. Now think about if we did this backwards. If we go backwards, then we would be halving, because the opposite of doubling is halving. So this would be to the 1/2, to the 1/4, to the 1/8, which, going back to our exponent rules, that's what we've learned. 2 to the negative 1 power really means the reciprocal of 2 to the first. So that would be 1 over 2 to the first. 2 to the negative 2 is the reciprocal of 2 squared. So that's 1 over 2 squared, which is 1 over 4, and so on and so on. Okay, so when we look at this, you can see that y equals 2 to the x versus y equals 1/2 to the x are similar, but also different. One is exponential growth and one is exponential decay. But because 2 and 1/2 are reciprocals of each other, you can see how they reflect over the y-axis there. Something I talked about earlier was this tail that all exponential functions have. That tail, where it kind of planes out, it's like its little plateau, has a very special term called the asymptote. And what an asymptote is in mathematics is imaginary line the graph approaches but does not touch or pass through. And as you get into higher mathematics, you're going to work with a lot of different functions that have these imaginary lines there that are asymptotes. So in this case, these have an asymptote at y equals 0. Finding the asymptote helps you to state the range. The domain of all exponential functions is all real numbers. However, the range is always restricted. It'll never be all real numbers, because as you look at these graphs, what you notice about both of them is that the range is all positive real numbers. Remember, ranges are y values. So we say that the range is y is greater than 0 or the positive real numbers. Wherever your asymptote is, that helps you to be able to state your range. In tomorrow's lesson, we're going to focus a little bit more on graphs and moving these graphs up and down and what the effect of the asymptotes. But let's finish up today's lesson. Okay, so for today, what we're going to do is just a very small assignment on if you're giving a set of data, could you write the function? So it says determine whether each set of data displays exponential or linear behavior. then write a function that represents the data. So the first thing we want to do is make sure our x's are increasing at a constant rate. You don't want to see the behavior in your x's. The behavior should always be in your y's. So what we can see in this one is as we look at our y values, we can see that they're multiplying by 3. Because this is a multiplicative behavior, this particular function is exponential. Because it is multiplying by a number greater than 1, we would say that it is exponential growth. So what we need is we need the multiplier, which we can clearly see is 3, and then we need to know the y-intercept. In this case, we cannot see the y-intercept because it doesn't show us when x is 0. So all we would do is just work backwards. So if we come over here and we go back 1, instead of multiplying by 3, we would divide by 3, and we know that 3 divided by 3 is 1. So just like you learned y equals mx plus b, folks, you've got to learn y equals a times b to the x. That is your basic formula for writing an exponential function, where a is our y-intercept and b is our multiplier. So this equation will be y equals 1 times 3 to the x. And again, you can write it like this, or you might see it like this, y equals 3 to the x. Hey, it's just like the problem we did at the very beginning about the pay it forward. So let's check out the second one. Okay, in this case, if we look at the behavior of the function, our x's are going up at regular intervals, but in our y values, it's adding 4 each time. So would this be exponential or would it be linear? And hopefully we can see, because this is additive, this is a linear function. This would be a linear increasing function. All right, so we know to write a linear function, the formula is y equals mx plus b. So remember, to get our slope is the change in y over the change in x. So you got to come up here and make sure you've got your change in x too. So when we do the change in y over the change in x, the change in y is our 4, the change in x is 1, so that would give us 4. Also on this one, we cannot see the y-intercept, so we'd have to work backwards. So if we subtract 4 here, we can see the y-intercept was at 0. So this one would have the equation y equals 4x plus 0, or y equals 4x. And folks, one of the things you can do when you do these is pull up Desmos or your graphing calculator, type these in, and create a table and make sure the table matches the table here on the problem. All right, try the next two. And when you're done, restart the video to make sure you did them correctly. Okay, hopefully you can see that the third one here is linear because in the y values it has an additive behavior. So because it's linear, we find the slope, and the slope is that it increases, the y is increased by 6 as the x increases by 1, so that's 6 over 1, which is 6. And we get to see the y-intercept because we know that's when x is 0, so the y-intercept's 3, so we have the equation y equals 6x plus 3, just like we did several weeks ago in class. This one, when we look at the y values, the behavior is multiplicative. So that's what makes it exponential. So our y-intercept is 4, our multiplier is 2, therefore our equation is y equals 4 times 2 to the x. I know that this was kind of a longer lesson, so you're going to have a very short delta math. One wrong, you got to keep trying, and all it is going to be where they give you a table and you figure out the equation. All right, so in this case, hopefully you can see that it goes from, don't even worry about the decimals, 2, 4, 8, 16. Folks, that is doubling. We can also clearly see the y-intercept right here because it's when x is 0. So we would say y equals 0.02. And then you're just going to pull up this little tablet right here and click times. It's kind of like Desmos. And then you're going to put your multiplier, which we could see was 2. And then you're going to say raised to the x power and submit your answer. Yes, I want to submit it, and yep, and it goes through and it tells you how to do it. So for those of you who've been struggling with this, you know, if you get one wrong, it tries to tell you what to do, but in this case we have the correct answer. Last but not least, I just wanted to show you all this graph with everything going on with the coronavirus. I actually watched this on the news last night with the White House briefing. So this was the different states in the United States and the number of cases of the coronavirus by 100,000 for all states. And what you're seeing here is a bunch of different exponential curves. So New York, obviously, the problem was they didn't put in the sanctions that we have early enough. And so they've already hit that part where it really just started to take off. And that's what exponential functions do. They might start out really, really, really slow. Like look at here at this f of x equals 2 to the x. Do you see how it's almost flat right here? But once if they keep doubling, they finally take that turn and multiply. And for those of y'all who were able to watch that news clip the other day, that's what I wanted you to understand about exponential functions. Once they take that turn, they grow really, really, really fast. So you can see New York has the most cases, where when you look right here at this orange one, this one is New Jersey, which of course they're right side by side. And it's got about half as many cases as New York. But again, they took that exponential turn a little bit closer to other people. Now, of course, these aren't perfect curves because in the real world, nothing ever falls perfectly on a line or on an exponential function. So these are the regression models that match it. But you can see where these states that did put in the sanctions of everybody staying home and kind of shutting down everything, as crazy as this is, they're not increasing as fast. All right, so do your little assignment in Delta Math, and tomorrow our lesson will be shorter, but then you'll have a bigger assignment. And tomorrow's assignment will also include more exponent rules. It's going to be kind of a little assessment of it all put together. Have a good day.